This Wolfenstein 3D style shooter is written in pure Python using modern OpenGL. And if you are familiar with my channel, you probably paid attention to the video about the creation of such a game, but then I used software rendering in the old-school ray casting technique, which necessitated the use of various mathematical tricks, and also imposed a number of performance limitations. But in this video, I would like to share my dev story on how to make such a shooter in a more modern way. That is, by adopting the OpenGL pipeline we can get all the power of the GPU, and at the same time you will see that for this kind of game it is enough to use quite straightforward approach in the most basic data structures. Moreover, for creating levels, placing items and enemies, I adapted the use of the tiled map editor. Although it is intended for creating 2D games, it perfectly suited this shooter, which ultimately allows you to quickly and conveniently create new levels and content for the game. And to create this project, the following stack of frameworks was chosen. I used the Pygame library to create an OpenGL context, load assets and handle events from input devices. In turn, the ModernGL module was chosen to manage the OpenGL context, and along with it, the GLM library made it possible to quickly and conveniently work with vectors and matrices, and the Numpy library was used to work with polygonal meshes of objects in this game. And so let's imagine that we are at the initial stage of development of this game, and see what we have to go through to get the final result. And by initial stage, I mean that you have already done the routine part and organized your code to interact with the OpenGL pipeline in such a way that we can render a simple quad on the screen. In fact, such a quad will be the basic entity for rendering almost all objects in the game, and when composing its mesh, it is most convenient to place the quad in a local coordinate system so that the origin is in the middle of the bottom of the quad. And as for this initial setup, its architecture is quite simple. We have an application class that initializes the OpenGL context and an instance of the engine class. And in turn, there is a player class, its parent class is camera, there is also a shader program class and a class for working with textures, and of course there is a scene class, which will contain all the game entities. As you can see, almost all connections between classes are made in the form of a composition, and let's now look at such an important point as creating and rendering levels for our game. So, to create levels of our game the choice fell on the level editor called Tiled, although this editor is designed for 2D games, but because we are creating a game in the style of Wolfenstein 3D, for these purposes it will suit us perfectly. After installing this editor, we can start creating our test level. To do this, create a layer called walls, and it is important to note that the size of the tile in the editor is equal to the size of the textures for the game. In our case, all textures in the game will have a size of 256 pixels. And as you can see, there are no difficulties when working with this editor, and the next task for us will be to create a parser for the file format of this editor. After saving the level we now have two files. The first contains information about the textures used, and the second file contains information about the geometry of our level. And to make it easier for us to parse this data, we will use the PyTMX module created to work with the tiled editor file format. And then we can create the level map class, with which we will load our level files and get all the necessary data from it. And to store level data, we will use a data structure such as a hash map, and in Python a dictionary is just suitable for this. In general, let's create a hash map for our walls. We store tile coordinates as keys, and texture identifiers as values, and let me explain why all this is needed. Take another look at our walls, and our task now is to create a single three-dimensional object that this map will represent. And I propose to imagine each tile as a large voxel. Given that the channel already had a video on creating a voxel engine, we will borrow some approaches from there, only in our case we need to create only one layer of voxels. So, we will create a mesh of walls. It's not really a voxel, and each tile representing the walls will have 4 faces. Each of them is a quad consisting of 2 polygons, and our task is to correctly describe the order of vertices for these triangles. But at the same time, we don't need extra geometry that will be hidden from our eyes. And the creation of such a wall mesh is implemented in the Level Mesh Builder class. Here in the build mesh method an array of vertex data is created, and by iterating over the coordinates of our level, we use the wall hash map to determine whether it is necessary to create wall faces here, while the isBlocked method helps us cut off invisible geometry level from the player's point of view. Also from the hash map we get the texture identifier and, in addition, each face has its own unique ID. In general, these values, along with the vertex position, become attributes of the vertex array object, which is formed in the level mesh class. And so we have these attributes at the input of the vertex shader. There's a trick you can use here to generate texture coordinates. These coordinates are stored in a separate array and there is also an array of indexes to it. So, depending on the ordinal number of the vertex and the parity of the face identifier, we can easily obtain the correct texture coordinates. And in the fragment shader, all that remains is to select the color from the texture, and I will note here that all the textures of the game will be stored in one texture array, where we select the desired one based on the texture ID, but we will return to this a little later. And thus our drawn level in the 2D editor became completely three-dimensional. And from the advantages of this approach, it can be noted that all geometry invisible to the eye is cut off, and the CPU only needs one draw call to render the entire level. And by the way, we can set the player's spawn location on the map. To do this, create a separate layer for objects, and we simply set the appropriate label as the only object on this layer. And in our parser, knowing the name of the layer, and since we have a single object, we will extract the position of this label using the pop method, and then calculate the position of the player in our game world. So, now the player is inside the level, and we did this only because our Wolfenstein clone will have textured floors and ceilings, although I try to stick to the style of the original game, but it seems to me that there were no textured ceilings there only because of the weak hardware for those times. And as for the floors and ceilings, in the editor for each of them there will be its own layer with the appropriate name, and at the moment for these layers we will simply tile the entire map with our texture. And just like for the walls, we will create hash maps for the floors and ceilings with their coordinates and texture IDs. And to build their mesh, we will do the same, but in order not to create unnecessary geometry, we need to make sure that these tile coordinates are not in the hash map of the walls. And as you can see, we now have textured floors. Using the test texture we can also ensure that the texture coordinates are correct. And as you can imagine, for the ceilings we will do the same, and this way we get a completely textured level. I would also like to point out that since our game is completely three-dimensional, we will not limit camera movement only in the horizontal direction, and let's now talk about texture handling. As I mentioned earlier, all textures are in one texture array. And for this purpose, the corresponding textures class was written, with the help of which the texture array is loaded into the GPU, filtering settings are set, and the texture unit is assigned. But the array itself is formed using a separate texture array builder class. Everything works as follows. Textures with names in lexicographic order are added to the appropriate folder, and using the method of this class we obtain a texture array and sprite sheet. And this sprite sheet is used in the tiled editor because I encountered problems loading a texture array with more than 128 textures into it. So, we selected suitable textures, formed an array of them and loaded the sprite sheet into the editor. Of course, there was an option to manually add textures, but why do it when you can automate everything? And now we can use our creativity and style our level as Wolfenstein 3D. And so our 3D level looks pretty cool, but since we're working with OpenGL, we still have the opportunity to make some improvements, and I'd like to touch on the topic of lighting. And let's take a look at our level in the case where we used only one texture of a uniform color. Obviously, now it is not possible to make out the geometry of the level, since everything merges into one color. But here we can resort to another trick and create fake diffuse lighting. To do this, in the vertex shader we use an array of shading coefficients for each of the faces, and since we always know the face ID, by applying this coefficient to the resulting color in the fragment shader, we can easily implement this type of shading. And this way we can now distinguish the details of our level, but since we used a voxel approach to create the level mesh, we can also take one of the shading techniques used even in Minecraft, and I mean such a shading model as ambient occlusion. And for voxels, there is a fairly fast and elegant way to calculate ambient occlusion. The main idea is to calculate ambient occlusion for each vertex using only information from its adjacent voxels. And for each vertex, depending on the location of these voxels, there are only 4 possible ambient occlusion values presented on the screen. So, to calculate ambient occlusion, we will use the appropriate method, in which for each face we check the presence of adjacent voxels, and since our level is one layer of voxels, then to calculate the coefficients for the vertices of the side faces we need to check the presence of only 2 adjacent voxels. But using this method alone will not give the desired result, and we will encounter the so-called anisotropy effect. And therefore you need to choose a consistent orientation for faces. This can be done by comparing the ambient occlusion terms for each face and selecting an appropriate orientation. That is, in this case, we flip the order of the triangle vertices for each face. But when changing the order of the face vertices, we should also assign the correct texture coordinates. And to do this, we will supplement the array of indices of these coordinates for cases of vertex flips. In addition, we will have the flip ID attribute, with the help of which we will obtain the desired index for texture coordinates. And as a result, we get a rather interesting shading model. Its main advantage is that it is calculated in advance and does not affect the performance of the game. And let's look at the level from a different angle, and for comparison, let's see what effects the use of shading gives. And besides, the model itself looks quite worthy to be used for a Wolfenstein clone, and if we add a little fog, we will get a completely atmospheric picture and as if we are in a dusty bunker. But our bunker is currently missing one important detail such as a door, so let's move on to looking at their implementation. So, in the editor, doors will be a separate layer of objects, and here we will agree that we will place them only between 2 walls. And if you look at the texture of the door, it is obvious that the movement of the door is planned to be in a vertical direction, and it will be approximately the same as you can see in one of the secret Doom levels dedicated to Wolfenstein. And since we are talking about game objects, the corresponding class will be useful to us. Among its features, we can note the following. For convenience, we will place any object in the game in the center of its tile, and we will also need a method for calculating its model matrix. And in turn, the door class inherits from the game object, and at the moment we are only calculating its model matrix. And then, when parsing door data, we first go to the coordinate system of our world, and then create a hash map of doors, where instances of the door class are assigned to the hash map values. And now I would like to talk about the peculiarities of rendering such objects. When we create large levels with a large number of items, enemies or doors, the naive approach associated with the fact that we will make a separate draw call for each object will quickly lead us to a dead end, since the application performance will be decreased with the growth of objects. The draw call itself is a CPU-intensive operation, so I suggest using the instancing technique for objects of the same type. And in OpenGL, this technique allows you to draw multiple objects with the same mesh in one draw call. And to implement instancing, we will have a class called InstancedQuadMesh, and to create its instance we pass a set of game objects in a shader program to the input of the constructor. Here we will use 3 buffers. The first is the quad vertex buffer, and the other buffers are for model matrices and texture IDs. And we create these buffers in a separate method by iterating through our game objects. And when creating a vertex array, we specify how these buffers will be interpreted. In our case, for each vertex, sequential values from the vertex buffer will be used, but for the model matrix buffer and texture IDs, we specify their use per instance. And when rendering, we need to specify the number of instances, which is equal to the length of the set of game objects. And thus, in the vertex shader for each quad there is now its own model matrix and texture ID. And with this approach, in the scene class we divided the door objects into 2 categories. These are the door objects themselves with their logic, and a separate object for rendering them. And when we run the program, we will see that all our doors placed in the editor are rendered perfectly, but for doors located in the editor for vertical walls, we are faced with a small problem. And for this case, we can check the presence of walls below and above the door, and accordingly rotate the door 90 degrees. And this will be enough for the doors to be positioned correctly. So, no matter how many doors are created, they will all be rendered in one draw call, and this is the main advantage of using instancing in OpenGL. And since we are moving like a ghost through our level, let's look at how to implement collisions with walls and doors. So, in the player class we process input events from the mouse and keyboard, and based on this we form a 2D vector for the next step since our movement around the level occurs in the XZ plane. Then we pass this variable to the move method, where for each of the components of the next step vector, taking into account the given size of the player, we calculate the position of the tile on which we can end up after taking the next step. And all we have to do is check the position of this tile to see if it is in the hash map of walls or doors. And in this simple way we can handle collisions in our game. But let's go back to our doors again, and look at the logic that will allow us to interact with them. And for this, in the door class we will define two attributes, one responsible for the state of the door being closed or not, and the other whether the door is in motion. And to interact with doors using the appropriate method, we just need to calculate the position of the tile where we are looking, that is, this is our position taking into account the forward vector. And if we look at a tile with a door, we activate its flag for movement. And we will call this method when the corresponding key is pressed. And then in the update method of the door class, we will place logic that will check what position the door is in and close or open it accordingly. And after the animation of the door movement is completed, we change its state from closed to open or vice versa. And in this case, we can now control the doors, but as you can see, we cannot go through an open door. And by making minor changes to the collision checking method, we got a fully working mechanism for interacting with doors. Well, let's now move on to the stage where we'll start populating our game with various objects, and we'll start with placing and rendering items in our world. So, we added images of the items we need to our set of textures. And now in the editor, on a separate layer of objects called items, we will place them. Parsing this layer is no different from previous actions, and we also create a separate hash map for the item's objects. And the item class itself is now almost the same as for doors with one exception. We will now specify the scale for each item. And in this case, firstly, we should describe all textures in a separate enum class with unique IDs, and here they should be ordered in the same way as in a texture array. And secondly, we will create a dictionary to describe the item's settings, where we will indicate their scale and some value that we will use later in the game. And as you might guess, the instancing technique is also used here to render all the items, just like for the doors. But using the same shader program as for the doors, we won't get exactly what we wanted. Our items look like flat textures, and here we should turn to the billboarding technique used in OpenGL. To do this, in the vertex shader we should calculate the model view matrix, and if we zero out the elements in the first column of this matrix except for the first element to preserve the scale, then we will get our items always facing us and rotating around the y-axis, and this type billboarding is called cylindrical. But it also doesn't quite suit us, and if we do the same with the second column of the model view matrix, then we will get spherical billboarding, the effect of which is quite close to how we see sprites in Wolfenstein 3D. But there is another problem hidden here. When we place many items, we can see how their quad in which they are rendered becomes opaque to other objects, and the simplest solution would be to cancel those fragments whose transparency is below a certain threshold value. And now that we have a proper way to display billboards, we can now do some of the items' logic so we can use them. And it is obvious that the player will have such attributes as health and ammo, and on each frame, for convenience, we will determine the position of the player's tile. And if this position is in the item's hash map, then we will accordingly access an instance of this item, and depending on its type, we will replenish ammo or health, and then remove this item from the hash map. And thus we have the opportunity to collect items, but we have no idea how much health or ammo we have, so let's figure out how to implement such an important point in games as head-up display. And for rendering head-up display elements, along with the existing assets, digits, textures, and a texture with the abbreviation FPS have also been added. So, the structure of this display itself will contain 12 separate elements, that is, we will use 12 quads to render it. And we will place these elements in the normalized device coordinate space. And as for the HUD elements, they will have their own settings, where for each element the scale and its position in NDC space will be set, while these positions are correctly adapted only for standard resolutions with an aspect ratio of 16:9. So we have a HUD object class where we get these position and scale values, and the model matrix is calculated. And the creation of these instances is carried out in the HUD class, where each object is added to a common list of objects so that we can also apply the instancing technique to them. And there is also a method for calculating digits values, which we call in the update method in order to calculate the corresponding digit for each quad and assign the same digit texture. And as for the vertex shader, only the model matrix is used to calculate the position of the current vertex, since we used NDC space coordinates. And when we implemented the head-up display, we now have current information about the player's health, the amount of ammo, and can monitor the performance of our game, and all this is done in a rather nice style. And as for performance, due to the work of the screen capture program, an incorrectly low frame rate is currently displayed, but you can see the current frame rate from this video. It is quite high and stays around 1000 frames per second. And for now, let's talk about one more integral element of the game, and by this I mean the player's weapon. So, at the moment, the game is supposed to use 3 types of weapons, and their textures have been added to our set of textures. Here we have 5 textures for the animation of the shot of each of them. And in addition to general settings for weapons, we will also have individual ones that determine their characteristics. And the weapon class itself is quite similar to the HUD object except that it has attributes and a method in which the shot animation is performed based on the use of the player's shot flag. There is a separate class for rendering weapon. This is the same quad mesh, and for rendering animation we will have access to the weapon class from where we need to know its ID and the current frame for animation. So, in the player class, in addition to the shot flag, there is a dictionary for the arsenal of available weapons, and as you can see, the starting weapon will be a knife. You can switch weapon types either using the keys or by scrolling the mouse wheel, and the shot itself is fired by pressing the left mouse button. There is a method for switching weapons and there is a method for firing a shot, the logic of which is quite simple. Depending on the type of weapon and the presence of ammo, the shot flag is activated and the corresponding ammo consumption occurs. And at the moment in the level editor we can add our weapon icons to the items layer, but at the same time we will have to supplement the method for the case when we take such items. And so now we have weapons in the game, we also have stabbing animations and we have weapon switching, and we can fire shots and see their animations. But at this stage one would like all these actions to be accompanied by an appropriate sound, so let's see how we can implement this. And as for sound, we can create a class of the same name, where we will define the number of sound channels, and then simply load the samples we need for all cases of sound playback. And the main method will be to play sound on the appropriate channel. And this multi-channel will ensure simultaneous playback of sounds equal to the number of channels. And now when certain events occur in the game for which we have samples, then we start playing this sound. Well, we have come to the moment when we would like to see some action in our world, so let's figure out what we need to finally create enemies and arrange a shootout with them. So, textures for enemies will contain animations of walking, their attacks, taking damage and dying, but the number of textures for each type of animation may be different for each type of character. To place enemies, we will agree that we select the first texture from their set. We also place them using a separate layer in the editor called NPC. After adding enemy textures, don't forget to give them names and assign IDs. And we will also have settings applied to NPCs. One of the features here I would like to note is that we manually determine the number of frames for each animation, as well as the frame numbers from which these animations begin. Also, like doors and items, our NPC class inherits from GameObject, and parsing these objects in creating their hash map and mesh is done the same way. So by placing enemies in the editor, we can now render them in-game with just one draw call. And let's briefly consider what logic our enemies may have. So, when initializing an instance, we get all the settings specific to the type of this NPC. We also create the necessary attributes for the animation, set the type to the initial animation in the walking state, and animate it. We can make sure that the walking animation works correctly, and let's now consider the case where the NPC will go into attack mode. And in order for the NPC to understand that he saw the player, then for this we need some kind of ray casting algorithm, and here we will borrow the same approach that was used when creating the voxel engine. And the implementation of this ray casting is based on an article called Fast Voxel Traversal Algorithm for Ray Tracing and published back in 1987. So, the entire attack logic will be activated based on the flag whether the player has been noticed. To do this, we will cast ray from the NPC position towards the player, and in this case we will activate this flag and play the specified sound.
Point. Point. Point.
And as you can see, when a player is detected, a set sound is played, but in order for the NPC to begin meaningful pursuit of us, some pathfinding algorithm will need to be used. And since we do not have moving costs, we can use the breadth-first path search algorithm for these purposes. This algorithm is implemented in the Pathfinder class, and its task is to find the shortest path to the player and give us the tile position to follow along this path. So, when we have the coordinates of the tile to the player, then the NPC will move through the center of the tile, while we will also take into account collisions with walls so that he does not walk through them, and give him the ability to open doors. And in addition, we will add a condition to the collision processing method so that NPC are not in the same tile at the same time. But since the enemies are now moving, in the engine class we need to rebuild their hash map, and we will only be interested in the remaining living entities. And thus we can now play catch up with the enemies, and it looks quite funny, especially when you are trying to close the door from them. And the NPC will attack when the distance to the player is less than the value set by the settings, while we again raycast to make sure there is a direct line of sight between the player and the enemy, and here we use such a characteristic as the probability of an NPC hitting, in which case damage is caused to the player. And at this point, we can make sure that with line of sight, enemies attack us, chase us and deal damage, but our player now remains immortal. And for this we will have a method to check health, and in case of death we restart the game. And also there will be a method to check the hit on enemies. Here we also use the probability of miss and raycast the enemy, and if there is a direct line of sight, then damage him. And so our game is almost ready. We have full interaction with objects and enemies of the game world, but in addition to shooting we can move to the next level in the following way. Let's say you have created several levels. And one of the ways to complete one level and move on to another is to find a key that opens a special door. And in the code it looks like adding a couple of conditions. By the way, the full source code of this project is available at the link in the description. And in the end, in this way you can create an unlimited number of levels, and as you can see turned out quite a nice clone of Wolfenstein 3D, which was quite easy to implement having a basic knowledge of OpenGL. And in addition, the engine performance remains quite good, so there is room to create very large levels or realize beautiful effects. So create your levels, play the game and leave comments.